So yesterday we started talking about projectile motion. Okay, and we talked about the two types of projectiles. There are horizontally projected projectiles, right? That's like a car that drives horizontally off a cliff, or a person who runs horizontally off a diving board, okay, or whatever. They basically have no vertical component to their movement at the initial point. And then there are projectiles that are projected at an angle. All right, so in this case, or sorry, then we have projectiles that are projected at an angle. They do have both a horizontal and vertical component at the initial point because they're moving obviously above the horizontal, or in some cases, below the horizontal. Okay, if I was standing at the top of a building and I threw something at an angle downwards off of it, it would have both a vertical and a horizontal component, but okay, it would be moving downwards instead of upwards. Okay, everybody follow on that? All right, let's have a quick review of how the horizontally projected projectile works, and then we'll look at a different example of the projected at an angle. So I got a ball that rolls off a 1.2 meter high table. Right, so here's the table, and it is 1.2 meters high. So whatever falls off of it is going to fall 1.2 meters. It hits the floor 0.85 meters from the base. What speed did it roll off at? Okay, does that seem like it gives me very much information? No, but it actually gives me two other pieces of information, at least for the vertical perspective. What are they? Gravity gives me gravity, so our acceleration will be 9.81 meters per second squared, but it doesn't give me time. It gives me initial velocity. If it rolls off the table, it's not moving vertically when it gets off the table, at least not at time zero. All right, with this information, can I calculate time? Yes, I can, right? So this is going to be our vertical information, and over here will be our horizontal. Remember, for all projectile motion, we have to write those parts separately because all they have in common is time. All right, so all we know right now for the horizontal part is that the distance traveled is 0.85 meters. So looking for time here, I'm going to need to use d equals vi times t plus 1/2 at squared. This is 0, so I can get rid of it. Okay, a will equal d divided by half. Sorry, I'm looking for t. T will equal the square root of d over half of a. Right, that's the manipulation of that, right? Divide both sides by half of a and then square root. Okay, so t will equal the square root of 1.2 meters divided by 1/2 of 9.81, which is 4.905. Okay, is this thing falling for very long? No, it's like a fraction of a second. It doesn't take long for something to fall, less than a meter. So we got square root of 1.2 divided by 4.905. Okay, so it's fallen for half a second. Okay, can I figure out what speed it rolled off at? Because horizontally it's not accelerating, we can use this formula, v equals d over t, 0.85 over 0.5, and we've got our answer. All right, is that ringing a bell for everybody? Okay, for all projectile motion, we need to separate the two parts, the vertical and the horizontal. For any horizontally projected projectile, vi is 0. That's one of the things you just have to remember. Okay, for a horizontally projected projectile, it is not moving vertically at the beginning of the flight. Okay, its initial vertical velocity is 0. Okay, now if you recall, the other day I was telling you how CG had ruined an entire generation of physical perception in people. Okay, so I'm going to show you what jumping cars looked like before there was CG, because it was way better then. Yes, there was some tragedy because some cars got destroyed, especially the ones I'm going to show you. Okay, but it was obviously much more realistic because, well, it was actually a car being jumped. But a lot more effort goes into that then. You have to build the ramp, you have to plan the jump, you have to know what speed you want it, you have to distribute weight in the car so that it flies in the way you want and lands the way you want. Not that you're expecting it to survive the landing, okay? But you want it to land in a certain way so it looks good. Okay? The whole way to make a car look like it had jumped successfully back in the day, okay? And I mean like, you know, before CG, was to cut away right after it lands or the instant before it lands. Because if you cut away the instant it lands, sometimes you watch the car be destroyed. So what they would do is the car be flying through the air, and then just at the moment it was going to hit the ground, they would cut to another shot where the car is driving away. Okay? And if they timed it right, it looked like the car had successfully landed and not destroyed itself. So I'm going to show you a whole bunch of jumps from the original Dukes of Hazzard. Anyone ever watched the Dukes of Hazzard? And I don't mean the movie, which was an absolute travesty. Okay? Willie Nelson is not Uncle Jesse, and Stifler is not. It's just terrible. Anyway, yeah, don't watch the movie. It's 2 hours of your life you'll never get back. Okay? But the original show, pretty funny, actually. Terrible acting, but lots of car chases, which makes shows good. All right. Okay, so the start of this has us looking at a projectile, the General Lee in this case, okay, being projected 20 degrees above the horizontal at 32 meters per second. Okay, that's the velocity it leaves the ramp at. It's going 20 degrees above the horizontal at 32 meters per second. That's like 125 kilometers an hour. Okay, all right. The General Lee obviously follows a normal projectile arc until encountering the riverbed on the other side. We won't say landing because, well, that would be definitely a euphemism for what happened. Okay, so this is the arc. This is what we got to figure out. We've got to find how far horizontally the General Lee is going to travel. Okay, so the stuff we know is this. Vertically, we know the acceleration is negative 9.81 meters per second squared. Okay, and since we have this vector triangle, we can find the horizontal component of its launched velocity, and we can find the initial vertical velocity of its launched component. Okay, so in order to find v horizontal, we're going to go cos of 20 times 32. And that'll tell us how fast it was traveling horizontally. All right, so we got cos of 20. Whoop, works better when it's on. Okay, cos of 20 times 32. All right, so horizontally, it's moving at 30.07 meters per second. Okay, and in order to find VI, it's the opposite side, so we'll go sine of 20 times 32. Okay, so that's going to mean our initial velocity is 10.94 meters per second up. So we'll say positive. All right, since both sides of the riverbed are the same height, how fast vertically is the General Lee going when it hits the ground on the other side? Right, the same speed it left at, because it goes up and back down the same distance at the same rate of acceleration. So in the perfect physical world, when it re-encounters the ground at the same height, it would be moving at exactly the same magnitude, but opposite direction. All right, that's what I can get for right now. If I want to find the horizontal distance, what else do I need? Time, right? Because horizontally, we know we're going to use v equals d over t. The horizontal velocity isn't changing. Okay, so all we need is time, and we'll be able to figure out how far it is across the riverbed. Can I find time with vi, vf, and a? Yes, I can use my Science 10 acceleration formula, okay, and go a equals vf minus vi over t. That would mean that t equals negative 10.94, our final velocity, minus 10.94, our initial velocity, divided by negative 9.81. Obviously, you wanted to do that shorter, you could just go 10.94 times 2 divided by 9.81, but I'm typing it in the way I wrote it on the page, okay? All right, so we've got a time of 2.23 seconds. All right, that I can move over here because it is the only thing the vertical and horizontal parts have in common. Now I can calculate the horizontal distance. D equals V times T, which in this case will be 30.07 times 2.23. Okay, so the General Lee flies 67 meters. That's more than half the football field. Okay, that's impressive. In fact, it's like 2/3 of a football field. Okay. So impressive to say the least. Survivable for the car, not so much. Okay, and like we said, a lot of stunt drivers in there. Okay, and they would definitely grip the wheel, thumbs on top. Okay, otherwise you get your thumbs snapped off, which actually often happens in an accident if you're driving a car that doesn't have an airbag, which probably is none of you guys anymore. Okay, a lot of times when people get in an accident, they would get their thumbs busted. Okay, because you'd move forward and just get them snapped back or dislocated or whatever. Okay, now the airbag actually pushes your hands off of the steering wheel when it detonates. Anyone ever been driving when the airbag goes off? Your forearms are bruised and sore afterwards. The force of the airbag hitting them actually will bruise you. Okay. Everyone thinks like the airbag's this nice pillow. It's so not. Okay, it explodes in your face. Okay, that's how it inflates so quickly. It's actually an explosion. Okay, it sounds like a gunshot, like right next to your face. Okay, it's very loud. All right, everybody follow how that one worked? The question asked us to do one other thing, and that was calculate the maximum height of the General Lee. So where does the maximum height occur? Halfway, yeah, right here, right? Right at the halfway point is where that occurs. Now, there's two ways to do this, but one of them people just never get right. And that is, I'll just divide the time in half, use half the time because that's when it occurs. But for some reason, people just never get it right when they do it that way. Okay. The other way to do it that works more often is to use just the vertical information, not the time. Okay. I'm looking for essentially the vertical displacement at this point. Okay. At any object's highest point, how fast is it moving vertically? Right, 0. When it's at its highest point, that's where it's slowed down and is now changing direction to come back down. So its final velocity at its maximum height is 0. So I know final velocity. I still know my initial velocity because that hasn't changed. Okay, and I'm looking for the distance. I also still know the acceleration because that hasn't changed. So I have VF, I have VI, and I have A, and I'm looking for D. So when I calculate the maximum height, I always use this formula. Okay, because I've calculated this, I know this is 0, and I know this is 9.81. So all I have to do is calculate D. All right, so that's going to be VF squared minus VI squared over 2A equals D. Okay, so we've got 0 squared minus 10.94 squared divided by 2 times negative 9.81. That'll give us our maximum height or our vertical displacement at that point in the flight. Okay, so we'll have divided by 19.62. 19.62 is 2 times 9.81. I'm just shortcutting here. Okay. All right, so it reaches a height of 6.1 meters. Roughly the equivalent of dropping a car off the top of the gym. Okay, so pretty high. Okay. It's a long way to fall. Okay, so our maximum height is going to be 6.1 meters. Okay, everybody all right with how that one works? Every year, I put a projectile motion question like that on the unit exam and the final exam. I have no intentions of changing said pattern. Is anybody writing that down? But I just told you that this is going to be a question on your unit and final exam. I sometimes I do. Sometimes I use a different car or a football or, I mean, the context doesn't matter, right? It's, what is it? What are we using, right? It's the same kind of question. Okay, now we're going to look at some examples of good, well, mostly bad movie physics.